If you throw a wrench through the air, it tumbles chaotically. But hidden inside that chaos is a single balance point, and if you track only that point, it traces a perfectly smooth, predictable parabola. Looking at this standard textbook definition, we call this the center of mass. It is the specific point where a physical system moves exactly as if its entire mass is concentrated there. Finding this single coordinate lets us ignore the unpredictable rotation of an object's outer edges, reducing a complex physical system into one easily trackable mathematical line. For two masses, the balance point sits closer to the heavier object, its distance inversely proportional to weight. Position R1 equals opposite mass m2 divided by total mass multiplied by distance d. The same logic applies to R2. If identical, the center snaps to the midpoint, d divided by 2. This basic one-dimensional balancing act is the foundation for everything else. Once you understand this proportional ratio, you have the logic needed to map much larger systems. Now, let's take that concept off the straight line and scatter multiple particles across three-dimensional space. To map them, we draw position vectors originating from coordinate 0. To find the collective center point, we use the vector sum formula. While the sigma notation might look intimidating, it represents a simple operation. It is strictly a mass-weighted average of all those individual positions. Looking at these separated equations, we see how easy calculating this actually is. You do not solve a massive 3D vector all at once. You just break it down into three isolated one-dimensional calculations, one for x, one for y, and one for z. No matter if you have 3 particles or 3,000, locating the center of mass is strictly a process of repeating basic multiplication and addition across independent coordinates. Let's apply this to a concrete problem: 3 discrete masses arranged in a triangle. The necessary first step is assigning strict Cartesian coordinates to each object. We set the 2 kilogram mass at the origin, 0, 0, placing the 4 kilogram mass at 1, 0. Finding the exact coordinate for the top 6 kilogram mass requires an extra step. By dropping a line down to create a right triangle, we can use basic 60-degree trigonometry to find its vertical height. Sine of 60 equals y over 1, which gives us an exact y coordinate of root 3 over 2. Now that we have all 3 sets of coordinates mapped out, pause the video. Take a moment to plug these values into the individual x and y formulas and calculate the final center of mass yourself. Checking the derivation on the right, here's how the calculation resolves. By substituting our specific mass and coordinate values into the respective formulas, the math simplifies down. For the x-coordinate, we get 7/12, and for the y-coordinate, root 3 over 4. When we plot that final point back on our grid, we see the actual result of the math. The center of mass rests suspended entirely in the empty space between the objects. It does not sit inside any specific mass at all. Looking at these reference shapes, we can observe a shorthand for continuous materials. Because a uniform solid distributes its weight evenly, it behaves precisely as if its entire mass is concentrated exactly at its geometric center. We can use this geometric property to solve complex bodies without relying on calculus. Take this solid L-shaped structure. It is composed of 2 distinct continuous segments, a horizontal rod with a mass of 2m and a vertical rod with a mass of just m. We treat the horizontal rod as a single point mass, resting squarely at its own center, coordinate L, 0. Then we collapse the vertical rod into a single point mass at 0, L over 2. With the solid shapes converted into basic dots, we plug them back into our standard formula. Running the mass-weighted average for x yields 2L over 3, and for y, we get L over 6. By recognizing that continuous objects can be treated mathematically identical to simple dots, we bypass complex integrals completely. This demonstrates the wide-reaching utility of the core formula we started with. Let's review the precise tools you now have. First, the balance point between any 2 masses is governed by an inverse weight ratio. Second, 3-dimensional systems can always be broken down into separate, independent 1D coordinate formulas. And third, uniform continuous shapes can always be swapped mathematically for single-point masses. Understanding the center of mass gives you a powerful framework for simplification. You now have the ability to strip away the unpredictable rotation of any physical system, reducing it completely to a single, solvable coordinate.